Hi, I'm Wang from Tsinghua University. I will introduce our new work, Deft, a scalable tree index for disaggregated memory. This is a joint work with Jing, Yuhao, and Professor Jiwu. To address the low memory utilization issue in data centers, memory disaggregation architecture is proposed. It physically separates the computing and memory resources into distinct resource pools, which are connected by high-speed RDMA network, as shown in the figure. In the figure, computer nodes are equipped with many CPU cores and a small local DRAM for something like caching. Memory nodes host a high-volume DRAM and a few of 1P CPU cores for control path operations, such as memory allocation and network connection. RDMA network is a key enabler of memory disaggregation. It provides high bandwidth and low latency network access. RDMA supports one-sided verbs such as raise, rise, and atomics such as compare and swap, and fetch and add. With memory disaggregation, CPU and memory can scale independently, which ensures high resource utilization. In this work, we focus on tree indexes on disaggregated memory. Tree indexes are key components for many DM applications, such as keyword stores and databases. We can use a tree index to retrieve data in disaggregated memory and performance range query. A DM-based tree index is concurrently accessed by multiple compute nodes, so the scalability is important. However, we found the current DM-based tree indexes suffer from two performance issues when serving many compute nodes. First, they are in a dilemma of I/O amplification and round trips. Tree-based indexes are designed with a huge node size and thus a low tree height to reduce network round trips. However, this leads to large I/O amplification and easily saturates the network bandwidth. This is because in the current indexes, clients must fetch the whole node's use RDMA rates before operating on it. For example, in the case of 1 kilobyte tree nodes and 16-byte QA entries, the I/O amplification is 64 times. The left figure shows the real throughput and the tree height of Sherman with different tree node sizes. Even with only one compute node, the NIC bandwidth is saturated when the node size is larger than 1 kilobyte, and then the throughput drops. Second, the concurrent control of current indexes has high overhead. When resolving read-write conflicts, they use node-level locks, which do not support concurrent updates and inserts to the same tree node, and it provides low performance on the skewed workloads. When resolving read-write conflicts, current indexes prefer lock-free reads since it can avoid locking operations for reads. However, it is challenging to design a correct and low overhead lock-free mechanism for DM indexes. It is worth noting that an RDMA RAID cannot guarantee data are fetched in increasing address order. Such a guarantee only exists in a single cache line. Under this constraint, the current lock-free mechanisms have high overhead. The checksum approach is computationally expensive and thus induces high latency. And this approach restricts the RDMA I/O granularity to a full tree node for recalculation. The versioning approach requires 3 individual RDMA rates for fetching an object, which cannot be combined or overlapped, since the read operations can be reordered. The cache line version approach needs three large writes to update all data and versions. Next, we will introduce Deft, a scalable tree index for disaggregated memory. This figure shows architecture. Deft is a B+ tree that stores data in the leaf nodes. Each compute node caches internal tree nodes to reduce remote accesses. Deft includes three techniques to improve concurrency performance. The first is the crafty tree node, including hash-based leaf node and segmented internal nodes. They reduce I/O granularity but not increases tree height. The second is a scalable one-sided share-exclusive lock, which supports concurrent insert and update operations to the same tree node. Finally, Deft designs an on-path decoupled versioning to enable efficient and correct lock-free rate. I will now describe those techniques in turn. For each leaf node, Deft organizes it into a bucket-based hash table, where each bucket contains multiple key slots. When searching a key, the client locates the associated bucket by hashing. To tolerate more hash collisions, Deft uses an overflow bucket, which are shared by two adjacent buckets. In this way, we fetch only two buckets in one read operation, and thus reduce the read amplification. For insert and updates, Deft uses RDMA casts to atomically write queue entries and reduce read amplification. Unlike leaf nodes, internal nodes need ordered searching. Deft redesigns them using the idea of lambda index. Each internal node is evenly divided into several subnodes. For example, this figure shows an internal node with the key range from 100 to 500. It is divided into 4 subnodes. Queue entries are sorted between subnodes, but unsorted within a subnode. We record the granularity, or the number of subnodes, in its parent node's point. In this example, when searching a key that equals 215, according to the key range and the granularity, the client fetches the second subnode. Next, it finds the largest key, not greater than k, then follows the point to the next level. By doing so, we fetch only one subnode in one read operations, and thus have smaller read amplification. When inserting a key pointer pair to an internal node, the client first fetches the associated subnode. If the subnode has free slot, the client inserts it with RDMA casts. If the subnode is full, we merge every two adjacent subnodes and updates the granularity in parent point. The figure shows how an internal node having 4 subnodes is merged. Improve the concurrency. Deft leverage one-sided share exclusive lock to perform insert and update operations. Before inserting or updating an entry in a tree node, the client acquires a share lock so that Deft supports concurrent write operations to the same node. If an insertion triggers node splits, the client upgrades the share lock to the exclusive lock. It is important to note that Deft uses exclusive lock for deletion to avoid duplicated entries caused by concurrent lock-free insertion and deletion. We implement the one-sided share exclusive lock using Lampert's bakery algorithm. A client obtains a ticket and then waits for its turn. The locks are stored in the RDMA NIC's memory. We use RDMA extended fetch and add to simplify the locking and unlocking operations. It supports the mask semantics and can add values on multiple fields independently. By leveraging it, we can avoid overflow to other fields when operating the locks, and can support upgrade share lock to exclusive lock using one RDMA fetch and add. To enable efficient and correct lock-free rate, Deft introduced a new mechanism called on-path decoupled versioning. As shown in the figure, In each tree node, Deft stores a data version at the beginning of each cache line and stores a commit version in the header. When a node splits or merges, the writer first updates the data with a new data version by one RDMA write, and then updates commit version to the new data version. For readers, they first read the commit version and then read the data with data versions. This involves two RDMA reads. The data is consistent if the commit version and the data versions match. Note that we only read the needed cache line rather than the whole node. Deft further improves the performance of our versioning approach by hiding the reads on commit version in the searching path. Specifically, as shown in the figure, we move the commit version from the header to the parent node's child point. By doing so, we can directly get the commit version in the search path of B+ tree and save an RDMA read operation. If the parent node is cached at the compute side and the versions mismatch, we invalidate the cached node and fetch it from DM. Next, we will report the evaluation results. The test bed consists of 10 compute nodes and 2 memory nodes. We compiled Deft with Sherman C, Smart, and DLSM. The Sherman C uses checksum to protect nodes in Sherman to ensure correct lock-free rates. Smart is an adaptive registry. DLSM is an LSM-based index. We use YCSB benchmark with A byte keys and A byte values. Each compute node has 1 GB DRAM for index cache. This figure shows the performance of insert-only workloads. The Deft is in blue. DLSM achieves the much higher throughput than other indexes, since it batches small writes at a compute size. However, it impacts data visibility. Deft is more performant than other indexes. In these update-intensive workloads, Deft outperforms than DLSM, Sherman C, Smart in throughput by up to 3.7 times, 6.1 times, 9.5 times, and 1.3 times respectively. This is because Deft's techniques reduce the I/O amplification and contention. As shown in those three figures, on the read-intensive workloads, Deft has the highest performance due to the low I/O amplification and the index cache consumption. For Sherman C, and DLSM, they are bottlenecked by the network bandwidth. For Smart, it requires more RDMA round trips for searching, since its index cache overflows. This figure shows the results of scan workloads. Deft has a similar scan performance to Sherman, since both leaf nodes of Deft and Sherman are unsorted. They have much higher performance than Smart and DLSM due to the compact structure of B+ trees of Deft. Finally, I give a brief summary. In this work, we analyze the inefficiencies of tree-based DM indexes and propose Deft, a scalable tree index on disaggregated memory. Deft is built with two key techniques. The first is crafted index node, including hash-based leaf node and a segmented internal node. They reduce I/O granularity but not increases the tree height. The second technique is the scalable concurrent control, which includes one-sided shell exclusive lock for fine-grained read concurrency and an on-path decoupling versioning approach for efficient and correct lock-free read. Evaluation shows Deft outperforms state-of-the-art tree indexes in both read-intensive and read-intensive workloads. Thank you for your listening.